Hello everyone, welcome to the lecture 17 of the Machine Learning Teach by Doing project. This is a very important lecture because in this lecture we are going to learn about one of the most important machine learning algorithms, which is called as gradient descent. Unlike other courses, uh, I am not going to start directly from the mathematical formula. I am first going to visually make you understand why this algorithm works in the first place, the motivation and the intuition behind this algorithm, and the visual introduction of how this algorithm works. Then, when we come to the mathematical algorithm itself, you will understand it much, much better. I actually spent quite a bit of time making the format for this lecture so that we have Python coding also in this lecture, and we have a lot of visual elements so that you never forget what gradient descent is. Okay, so this is also the part 3 of our series on logistic regression. In the previous parts, we have defined the hypothesis class for logistic regression, which is the sigmoid hypothesis. Then we have also defined the loss function in the previous lecture, which was the cross entropy loss. Correct? So, in this particular lecture, the main idea which we are going to explore is how to find the theta for the linear classifier which minimizes our loss function. Remember that the loss function is L, and L is a function of my hypothesis H and the true values yi, and H in turn is a function of theta. So how do we find the theta which minimizes the loss function? To answer this question, we will answer one more question. Let's say if there is any function f, let's say there is any function f of theta, how to find the theta which minimizes f? So how to find theta star which minimizes f? This is where gradient descent comes into the picture. People working in the fields of optimization have done so much work on gradient descent that now is the time when you must be thinking, why did we formulate machine learning as an optimization problem? The reason we did that is because we can define the loss function, and then we can optimize the loss function using gradient descent, based on which so much work has already been done in the past. So essentially, we convert the machine learning problem to an optimization problem. And since we have so many techniques to solve that optimization problem, we are now in comfortable territory. So let us learn about gradient descent and what it really means. The one thing which you need to know throughout this particular lecture, which I am going to write in a different color here so that we can come back to it again, is that a gradient of a function gives the direction of steepest ascent. I will further explain what it means, but for now, just keep this in mind. This is the intuition behind what is a gradient of a function, and this works in all dimensions, not just in one dimensional, two dimensional, but any dimension. Okay, so let us look at a practical demo. First, we are going to look at it in one dimension, and then we are going to move to two dimensions. Remember that the aim is that, let's say there is a loss function f. We want to find that particular theta which minimizes f. So my goal in this section is to show you why gradient descent is so intuitive, and why it is quite obvious that this is the correct algorithm which will work. And I'm deliberately showing this to you through a practical demonstration so that you will never forget it. So let us say in one dimension the function f, which we consider is f of x, is equal to x square. Let's say this is the loss function in one dimension, and our aim is to find that particular x, which minimizes f. Correct? That is the goal which we have. Now we know how this plot looks like, right? uh, let's say we know that all of us know this is a parabola which looks something like this. The origin is here 0 comma 0. Correct? This is x, and this is f, which is equal to x square. Now the main thing here is that, let's say you had no understanding of how this plot looks like visually. All you have is this function, and this may happen for complex functions, right? We would not know the visual nature of all functions. So imagine that you have no clue about this plot. I am just showing this right now for demonstration purposes, but imagine you had no clue how this plot actually looks like. Then, and also imagine that you were the first person in the world who were tasked to find the x which minimizes f. How would you go about solving this problem? Imagine you were living in a time when gradient descent was not invented. You only have this function and you want to find the x which minimizes this function. How would you go about it? Okay. The step one, which probably you might do as any person, is start with a random guess. This is quite easy, right? Anyone can do this. Start with a random guess. Let's say I start with an x1 whose actual value is equal to 9. In the plot, that x1 appears somewhere over here. So let's say this is my first guess which I have made. X1 is equal to 9. Now you only know that the value at x1, value of f at x1 is equal to 81. You do not know whether this is a minimum value, or whether there are other values which exist, other values of x for which f might be even lower. You don't know that at this moment. All you know is that you have started with x and you have found out that the f is 81. Now what do you do next? You want to find a different point after this point, correct? But you want to move in a direction which gives you a lower value of f. You cannot keep on finding these values, or you cannot keep on guessing random values of x. In the step 2, we want to move in a direction which actually decreases f from 81 to a value hopefully lower than that. And this is where we remember what we saw about the intuition behind a gradient. Remember that the gradient of a function always gives the direction of steepest ascent. So in this case, since it's one dimension, the gradient is also equal to slope. Since it's one dimension, the gradient is the slope of the function. And the gradient gives us the direction of the steepest ascent. Let me actually give you one more layer of intuition. Imagine that you are blindfolded and you are on a cliff, but the cliff is just one dimension. You can move either left or you can move to the right, and you want to get to the lowest point of that cliff. So, right now, our situation is that we have evaluated one point on the cliff, and you have seen that the value is 81. Now, you don't know whether to go to the left or whether to go to the right. Intuitively, so what you check is that you check that going left means that the ground is sloping downwards. So you are at a particular location on the ground, and you intuitively know that going left, you can see that going left the ground is sloping downwards, and going to the right the ground is sloping upwards. So you probably should not go to the right because the ground is sloping upwards. You should probably go to the left because the ground is sloping downwards. That is why you decide to go to the left from this point. One more way to mathematically view this is, since gradient is the direction of the steepest ascent, if we go in the direction of negative of gradient, that will be the direction of steepest descent. And this is exactly what you figured out, right? So going in the direction of negative gradient means going in the direction of negative slope is the direction of steepest descent, which means you're going down. Remember, you are a person, let's say, stuck in this one dimension and you want to know whether to go to left or right. You see that to your right, the ground curves up. To your left, you see the ground slopes down. So you should be moving to the left. You should be moving in the direction of descent. And negative gradient or negative slope gives the direction of the steepest descent. So you would want to move in that direction, correct? So the next x2, which you guess is not random, but you consider this factor and then you multiply it by the gradient. Basically, you move to the left hand side. From this x1, you move to the left hand side and you move in the direction of the gradient or the slope in this case, since it's one dimension. And what is this n? This n is the step size which you take. So remember that you are blindfolded on this place and you can only feel the slope. And now you decide you want to go to the left. That is correct. But how farther do you want to go? You also need to, you cannot take too large of a step. And you cannot take too small of a step either because it will take a long time to converge. So this is the value which you have to determine yourself as you explore. There is no way for you to right now find the true value for this. So I am going to call this as the step size. So based on this intuition, the x2 will be equal to 9 minus the step size into gradient. And as I mentioned, gradient will be just equal to slope, and that is the derivative of df divided by dx1. So let's say I say that my step size is equal to 0.15. We can choose it to be any value, uh, and derivative will be equal to, so if, since my function is x square, the derivative of x square is equal to 2x. Uh, so the value of my derivative at point x1 will be equal to 2x1. So my x2 will be 0.15 into 2x1, which is equal to 9 minus 0.15 into 2 into zero point 0.9. So it turns out that the new value is x3 is 6.3. So my x2 is equal to 6.3. So remember, we had an x1 here. X1 is equal to 9, and we move to the left. We move to the left and we move to x2, which is equal to 6.3. Again, very similarly, we look at the slope at x2 and we again decide to move to the left because on the right the slope is moving upward and we want to go in the direction of descent. So we again move to the left and then we will find x3 in a similar manner. So then x3 will be equal to x2 minus the step size into df by dx2. So this will be equal to 6.3 minus 0.15 into 2x2, and this turns out to be 4.41. So my new x3, I again move to the left, sorry, and I get an another value of x3. And if you project it again upwards, I again find the slope of x3, and I again see that to the left the slope curves downwards, to the right it curves upwards. So I again move to the left. I will continue doing this until I reach a point such as this, where I notice that whether I go to the left or whether I go to the right, it's not making much difference. It's neither curving upward nor it's curving downward, which means I'm in a stagnation situation, and I want to reach that stagnation situation, which is my minima. So if I keep on doing these iterations further, I will find x4, I will find x5, I will find x6, and ultimately I will reach x9, which will be almost close to 0, and all subsequent iterations after that will stay at that point, since I am in the stagnation zone now. So x9, so as I continue moving to the left, I will reach a point where x9 will be equal to 0, and even if I try to move left or right, x10 x11 will also stay 0. The function will neither show an increase nor decrease, which means I have reached a stagnation point, which means that I have reached my local minima. Gradient descent is as simple as that. Imagine you are blindfolded on this one dimensional hill, and you have to decide whether to move left or whether to move right. So, what you do, you first start at a random point, then you see in which direction the slope is curving. To your left, if the slope is moving down, you move to the left. To the right, the slope is moving up, so you don't move to the right. You always go in the direction of the descent. So you keep on moving to the left where it's descent, where it's descending, until you reach the stagnation point where the ground is no longer descending anymore. That is your local minima. And this is the gradient descent algorithm, which is as simple as that. And the way what we have done right now, there is a mathematical way to formulate this, which we will look at it just at this moment. So the mathematical way to formulate the gradient descent algorithm is this, and now you will appreciate it much better. It's actually very simple. You start with the particular theta, which is a random guess, which is theta initial. Okay, and the first iteration is t equal to 0, and then you continue a loop, which means you keep on iterating, and then you increase the value of t at each point. So if t equal to 1, which means we are in the first iteration, in each iteration you have to update theta. In each iteration you have to update theta, and the way theta is updated, minus f dash of, that's it. This is the gradient descent algorithm. It's as simple as that. This step is the most important. And you see, this is exactly what we kept on doing here, right? Whenever we found one point, how did we find the next point? We subtracted the step size multiplied by the derivative at that particular point. This is exactly what is mentioned here. When you have found, or when you have reached a particular point, you subtract the step size. So this is the step size, and multiplied by the gradient or the derivative at that particular point. Now your question would be, how long should we keep doing this? We should keep doing this until the value f stagnates, or the value f does not decrease too much further. And after you finish this iteration, you just return the theta, and this is the theta which minimizes f. So I deliberately did not start out with this mathematical formula, because first I wanted to show you that getting to this mathematical formula, it's actually very simple. All we are doing here is that at every point, uh, we are we have to move in the opposite direction of gradient, because remember, gradient gives us the direction of steepest ascent. So the negative gradient gives us the direction of steepest descent. That's why we have a subtraction term over here. That's why the subtraction term exists, because we have to move in the direction of descent, which is negative of gradient. And the reason the step size is introduced is that it's like, if you take a very large step size, you may shoot on the other side, right? Like imagine you started from x1 over here. uh, yeah, imagine you started from x1 over here and you took a very large step size, you might end up on this side of the function, and then again you might end up here, then again you might end up here, so you will keep on oscillating without ever reaching the minima. On the other hand, if you take a very small step size, it will take a huge amount of time for you to reach the minima. So the step size should be a balance between large and small. Okay. This is the gradient descent in one dimension, and I want to show you a Python code before we move to two dimensions. So whatever I have mentioned right now on the whiteboard, I have written a Python script here to simulate this exact same thing, and I will be sharing this script with all of you. The Python script is very simple. We start with a position of 9 as we did in the whiteboard. We use a learning rate of 0.15, which is the same value we used on the whiteboard. And then we use number of iterations equal to 10. So what I'm doing here is that you can see the new point is the current point minus the learning rate into gradient. This is exactly what we did here. New point is equal to current point minus learning rate into gradient. And then I plotted the value for every single iteration. So you see at iteration number 1, this is the point x equal to 9. At iteration number 2, we move somewhere here. At iteration number 3, we further move. So you see at each point we are moving to the left hand side. Initially we started at x equal to 9 and we keep on moving to the left hand side slowly. At iteration 3 we reach here, at iteration 4 we reach here, at iteration 5 we reach here, at iteration 6 we reach here, and you see at iteration 7 over here, at iteration 8 we are getting closer, and at iteration 9 we finally reach very close to 0, and at iteration 10 we exactly reach 0. So we have reached the local minima at iteration number 10. One way to visually see the way we are moving on the loss function is that our points are in one dimensional, that's correct. But if you see the loss function, we are always moving in a tangential direction. So the way to think about this is that if you actually, our points are in one dimension, that is fine. But if you see the loss function, uh, at every stage, so this is point equal to x1. To find x2 we moved in this direction, correct? Then we found x2, then we moved in this direction, then we found x3, similarly. So these directions are actually tangential. That's one more way to think of the gradient. So the gradient at a function is always in the tangential direction to that function. So we are moving in the tangential direction but in the negative of the gradient, because the gradient is the steepest ascent. So at this point, if you look at the gradient, uh, the gradient value will point in this direction. This is the steepest ascent, so we have to move in the opposite direction. That's why that negative sign is there. I'll be sharing this Python script also with all of you so that you can visually see for yourself. But please try running this script on your own. Don't just look at this video, but try running the code for yourself. It will give you so much intuition about what exactly is happening when we look at gradient descent. Now we will take one of my favorite examples of gradient descent, which is not covered too much in other courses. We will look at the gradient descent in two dimensions. Okay. So the loss function in two dimensions is, of course a bit more complicated. Loss function f, and f of xy, which we are going to look at, is x square plus y square. Okay. This is the loss function, and I want to find x comma y, or rather x star comma y star, which minimizes f. Now, first of all, how do you even start to visualize this function? Because this will be a three-dimensional function, right? Although x and y are in two dimensions, but this is equivalent to saying that z equal to x square plus y square, and that's equal to a three-dimensional plot. In one dimension, it was quite easy. F of x square, this was just a parabola. So for the explanation purposes, for me, it was very easy. But how do you explain this in two dimensions? Uh, so remember that z equal to x square plus y square, which is actually our loss function, will now be in three dimensions. And the way it will look like is what I have shown in this Python script. The way it will look like is this. This is the plot. What this means is that, forget about the red line here for now. What this means is that you take any x and y, there is a corresponding f. That's why it's a three-dimensional plot. And our aim is to find this thing. Our aim is to find this minima. You see, there is a minima at the bottom, which gives the lowest value of f. This point. This point. This is the local minima. Our aim is to find the minima here at the bottom, which we do not know right now. This is an amazing visual problem, right? This is visualization in three dimensions. I highly encourage you to run this script in Python so that you can visualize this script for yourself. Okay. So now what we will be doing is that, very similar to the previous thing, we do not know anything about this problem, correct? So let me make an initial guess. So let me make an initial guess, and my initial guess will be equal to 9 comma 7, and I have plotted this guess in this plot over here. uh, Here you can see this is my first guess, 9 comma 7, this point. And the loss function value for this point is shown over here. The loss function value for this point will be just equal to x square plus y square. So the loss function value will be 81 plus 49, which is equal to 130. Of course, this is not my minimum loss function, but I have to start somewhere. So I have to start here. Now let us use our learnings from the previous example, and let us say we want to move in the direction of descent. So let me say that x2, so initial guess x1, x2 is equal to x1 minus into gradient. Now the question which you all must be asking is that, now we are in two dimensions, right? So what does gradient really mean here? What does it mean? In one dimension, the gradient means the slope of the function. But what does gradient really mean in two dimensions? Here, you are blindfolded and you could go either left or right, correct? But in this particular problem, you can go straight, back, you can go in any direction basically, and you are still blindfolded. Imagine that you are on a hill. You can go left, right, front, back. In two-dimensional space, you can go in any direction, and you want to go in the direction which minimizes or which goes in the descent direction of that particular hill. So instead of the slope, we have to ask which direction should I go, which, so that I decrease the loss function most quickly. This is the main difference between one dimension and higher dimensions. In two dimensions, you have to ask the question. So in two dimensions, you have to ask the question, which direction should I go? Which direction should I go uh, to decrease the loss function, most quickly? So remember that in one dimension, there was just a line, right? And if you are at a particular point, let's say at x equal to 9, you could either go left or you could either go right. But in two dimension, you are somewhere here. Let's say the 9 comma 7 is somewhere here. So there is no left or right, there is just direction in space. You want to decide which direction should you go so that the loss function is minimized. Now, l- so you want to basically go in the direction which decreases the loss function most quickly, right? Which is that direction? Which is that direction which decreases the loss function the quickest? Um, so which is that direction which decreases the loss function quickest? In one dimension, we saw that it was the negative direction of the slope, right? But how to visualize this in two dimensions? Now I'm going to show you a beautiful visualization here. This is what is called as contour plots. Contour plots. Okay. So let's say uh, I want to visualize. So the three-dimensional plot looks like this, right? Three-dimensional plot looks like this. That's fine. But now, if you fix one value of z, if you fix one value of f, so let's say f is equal to 1. So this just means, so if f is equal to 1, this just means x square plus y square equal to 1. And that is a circle in two-dimensional space. So if I fix the value of f, I can show it in two-dimensional space as well. So let me show you the different contour plots in two-dimensional space. There can be, of course, infinite contour plots based on the value of f, correct? I'm trying to do my best here with respect to the drawing. Okay. So these are the contour plots, and let me zoom in further here. So let's say this corresponds to f equal to 1. Let's say this corresponds to f equal to 5. uh, and let's say this plot corresponds to f equal to 130. So remember that our first point which we started with is 9 comma 7, and for this point f is equal to 130. So this point will lie somewhere on this particular plot. So let's say this point lies somewhere over here. So this is my x1, correct? Now from here we have to decide which direction should I go so that the function decreases the quickest, right? uh, so imagine that this is f equal to 130, and let's say this is f equal to 140, and I want to go from x1 in the quickest possible way from 130 to 140. Which direction should I go? Let's say the problem is simple. I want to go from x1, which is on f equal to 130, to f equal to 140 in the quickest possible way. Which way should I go? If I go this way, it will take me this much. If I go this way, it will take me this much. It turns out that the quickest possible way is the perpendicular way. This this way is the quickest possible way to get from f1 to f2, 130 to 140. So this is the direction of steepest ascent. So this is grad f. This is grad f. Grad f is the direction of steepest ascent. So this you see is perpendicular here. This value. So this direction is of the fastest ascent. So if I am at x1 and if I want to move very fast upwards, so to increase f, I know which direction to go, this perpendicular direction, because it takes me the fastest to the next contour plot. But my question to you was, which is the direction you should go which decreases the function quickest? So now which direction should you go? The opposite, clearly. So you should go in the opposite direction, which is this direction, this. And this direction is in the negative of grad f. So here I ask the question, right? You need to know which direction you need to go instead of left or right. And now we have figured out that the direction needs to be in the direction of negative of grad f, because positive grad f is the direction of fastest ascent. So if the fastest ascent is this way, the fastest descent will be exactly opposite, which is negative grad f. So we need to go in this direction. So we need to go in direction of this vector. So if this is x1, we need to go in the direction of this vector negative grad f. Mathematically, the way to calculate gradient of f in two dimensions is very simple. It's a vector. The first value is the derivative with respect to x, and the second value is the derivative with respect to y. And this is also called as partial derivative, since there are two variables. So let us see what this gradient actually means for the function which we have considered, is equal to dou by dou x. This is also called dou x square plus y square, and dou by dou y x square plus y square. Now if you take the first value, which is d by dx or dou by dou x of x square plus y square, y is not dependent on x, so that will be just 0. So then this value will be just 2x, and the bottom value will just be 2y. Since d by dy of x square will also be 0, so the only thing which will survive here is 2y. So the gradient at any point f grad f in two dimensional space is given by this. So gradient of f at 9 comma 7 will be given by 18 and 14, and this vector will point in this direction, the orange vector. So negative gradient 9 comma 7 will be equal to minus 18 and minus 14. This is the direction of steepest descent from the point 9 comma 7. So if you look at this point, which is point 9 comma 7 over here, the purple vector is the direction of steepest descent, and mathematically it is given by minus 18 and minus 14. Now we have a way to find the next point. So remember, I mentioned here x2 is equal to x1 minus step size into gradient, and what this gradient was, it will just be equal to grad f. So the x2 will be is equal to x1 minus grad f at x1. Grad, I'm saying grad because it's also short form for gradient. Grad f at x1. So then, sorry, this step size I forgot, which will be is equal to uh, 9 7 minus step size is 0.15 into grad f, and grad f which we saw was 18 and 14, correct? So then it will be 18 and 14. We will use a step size of 0.1 over here to simplify the calculations. So then x2 will be 9 7 minus 1.8 and 1.4, which is equal to 7.2 and 5.6. This is my x2. So now I have started with an x1, uh, which was 9 comma 7, remember, and then I have decided to move in this purple gradient direction to give me x2. and my x2 will be equal to 7.2 comma 5.6. In three dimensions, the way it looks like is this. So I have started from this point here, and you see I have moved downwards here. So now you can see that I'm slowly moving towards the minima, which is at the bottom. So I started from 9 comma 7 seats, written 9 7 here. Then I moved to the next point, which is 7.2 comma 5.6. This is exactly what we had calculated here, 7.2 and 5.6. So similar to the case of one dimension, now I will keep on doing this. I will keep on finding x3, I will keep on finding x4, and I will keep on doing this until I reach a stagnation value, which will be my minima. Until I reach the stagnation value, which will be my minima. It turns out that for this particular example which we have chosen, we actually need around 15 iterations to we need around 15 iterations to converge to the minima for this particular example which we have chosen here. And the way this looks like in three dimensions is seen from the plot over here. You see, first we start from here, then we move downwards. Let's go further below. As I move further down here, you can see three iterations have proceeded, and I'm moving downwards onto this three-dimensional surface of the loss function. And when 4 points are there, I still am moving downwards, but I've still not quite reached the bottom. So if you see below, this is iteration number 7. Iteration number 7, I'm slowly reaching down, and I'm kind of at the bottom, but not exactly. And as you go further below, you will see that okay, this is iteration number 10, and I've almost reached at the bottom. And you will see that at iteration number 15, I'm completely at the bottom, which is my local minima. This is how I found my local minima through gradient descent in a two-dimensional input space. This is the beauty of the gradient descent algorithm. It works for any dimensions. So this same algorithm which I wrote before, right? Let's go here and let's zoom over here. This same algorithm earlier I had written for only one dimension, correct? But the only thing which now changes for multiple directions or multiple dimensions is this. Everything else remains the same. The loop remains the same. Uh, this remains the same. The only thing which changes is theta is equal to the earlier theta minus step size into gradient of f at theta t minus 1. You see everything has remains the same, but just we have replaced the derivative with the gradient. And what is this gradient of f in multiple dimensions? We saw that in two dimensions the gradient of f was just df by dx and df by dy in two dimensions. This same thing extends for more dimensions as well. So for three dimensions, the gradient of f will be a three-dimensional vector df by dx, df by dy, and df by dz or df by dz. If we move to 10 dimensions or higher dimensions, this gradient operator will just keep on increasing in size similarly. We will just have more variables. Here we added one variable. In 10 dimensions, we'll have 10 variables. But the mathematical representation of the gradient descent algorithm is just given by this one command. And I hope that now you understand how this command works, not just in one dimension. Here you saw how it works in one dimensions, but I made an effort to show you how this command works in two dimensional as well. In two dimensions also we can actually start from if our loss function is looks like this, we can start from a point, we can start from a random guess, and then we can use gradient descent to converge to the minima. And gradient descent is just quite simple, because see, in one dimension we have to decide whether we have to move left, whether we have to move left or right. So you are blindfolded in one dimensions and you have to decide whether to move left or right. In two dimensions you have to decide which direction to go in the xy space. So you can go forward, backward, left, right, anywhere you can go. So you need to decide the direction. So in one dimension the direction was just negative of the slope, but in two direction it turns out that the direction was negative of grad f, or the gradient of f in two directions. We also saw a very nice visual representation of what it means by a gradient of f. It means the fastest direction we can go from, the fastest direction of increase of grad f. Because if you are at this point, which direction should you go to reach to the next contour plot the quickest? And that's the perpendicular direction, which is exactly grad f direction, steepest ascent. So grad f is steepest ascent, but we have to go in the direction of steepest descent. So we have to go in the direction of this purple line. So mathematically the this vector is just 2x and 2y. So it is 18 and 14. And the purple vector which we saw will be just negative of that, which is minus 18 and minus 14. So we just update x2 by subtracting the step size multiplied by the gradient of f. So this is a vector operation in two dimensional space. This is a vector operation. In the 1D example, it was just a scalar, but now you can do the same for any dimensional space. For three dimension space, this will just be a vector of three quantities. It will be very difficult to visualize it in four dimensions, the loss function, because as human capabilities, it allows us to visualize stuff only in 3D. So I have restricted the visualization to 3D in this case. Okay, so this is the intuition for gradient descent, and this is the gradient descent algorithm which we studied right now. Using this same algorithm, in the next lecture, we are going to find the optimum theta um, for the logistic loss regression. Because now you have everything you need. You have the hypothesis, which is, let me zoom in here. You have the hypothesis which is the sigmoid, that is there. You have the loss function which is cross entropy, and you also have the algorithm which finds the theta which minimizes the loss function. Essentially now you have everything to find the optimal theta. So in the next lecture we will be looking at gradient descent algorithm applied to minimizing the cross entropy loss function using the sigmoid hypothesis. And we will look at how the gradient descent algorithm performs on the logistic loss regression, um, or the logistic loss classification. Thank you so much, everyone, for attending this particular lecture. And I hope you visually understand what gradient descent means now, and also mathematically understand it. I didn't just go through the mathematics, and I deliberately showed you these visual things so that you can clearly understand what we are trying to do here and develop an intuition for it. Once you have a strong intuition for gradient descent, it will help you in every single stage of machine learning, because this algorithm comes up everywhere, even in deep learning, even in back propagation. When we look at optimizing neural networks, the foundation lies always in gradient descent. So it's very important that you have this foundation strong. Thank you so much, everyone, and in the next lecture we will be looking at the last lecture of logistic classification. Thank you.